Hi there, Mr. Sutton here, bringing you the BC Calculus Chapter 7 Quiz 4 Extra Practice Solutions on Convergence Part 2. On this series, trying to see if it converges or not, I notice that I have this negative 1 to the n up here. That makes this an alternating series. And I also notice that as n approaches infinity, this nth term is going to decrease in absolute value to 0. So since I have terms that alternate and decrease in absolute value to 0, that means this series is going to converge by the alternating series test. On this problem, I notice that I've got something that's pretty close to a geometric series here, but not quite. So I'm going to try comparing this with a comparison test to a geometric series. I'm going to compare it to 1 over e to the n. And I don't really know what comparison test I'm going to use, direct or limit, going into this, but let's at least figure out what we have with us. So we've got, let's see, a geometric series here. Common ratio, absolute value is 1 over e. That is less than 1, which means that this geometric series test is going to say this converges. All right, so I have a series that converges versus this series. Now, to use direct comparison, this series up here, the original, would need to be less than this converging series I just found. But since I have a smaller denominator, I'm subtracting 2 in the denominator, that actually makes this a bigger series than my comparison series. So really my only option then is going to be to use limit comparison. All right, well, let me verify that I've got positive series here. So this series right here is going to be positive for n greater than or equal to 1. If you're doing e to the 1, e is still bigger than 2, so that's going to come out positive. And then this series here is definitely greater than 0. As long, again, as n is greater than or equal to 1, we're good. So now we're going to go ahead and take the limit as n approaches infinity of the ratio of these two series. So I'm going to have 1 over e to the n minus 2 in my numerator. And in my denominator, I'll just have 1 over e to the n. And I'm going to let all of this equal L so that I can refer to it very quickly if I need to. All right, same change flip this thing. We've got e to the n over e to the n minus 2. As n approaches infinity, I can forget all about this negative 2. So it's really just e to the n over itself, which comes out to a limit of 1. Now, since 1 is a finite positive number, since this L here is between 0 and infinity, and since my comparison series converged, that means my original also converges by the limit comparison test. For this problem, I'm trying to figure out the convergence of this crazy-looking series. Now, this is just essentially kind of a 1 over a radical n cubed situation. It's pretty close to that series, but it's not quite there, so I'm going to use one of my comparison tests to make this thing work. Let me start with my comparison series, though, 1 over the square root of n cubed. Now, this is really 1 over n to the 3 halves. So this is a p series then. My comparison series is just a p series with a p-value of 3 halves. Since that's greater than 1, I can very quickly say that this converges by the p-series test. All right, so which comparison am I going to use? Well, if I want to use direct comparison, I need to make sure this series is smaller than this converging series I just found. And as I look here, I'm adding stuff inside the denominator and there's no other change. So a bigger denominator is going to give me a smaller fraction for all n values greater than or equal to 1. So I actually can go ahead and use direct comparison on this, which is a little bit less work than limit comparison. So I also have to verify these are both greater than 0. The way I'll write all this then is 0 less than or equal to my smaller series, which is the original here, less than or equal to my comparison series. You could write either one of these. And again, that's going to be true for n values greater than or equal to 1, and we verified this. All right, well, since I found a series, or I have a series that's smaller than a converging series, that means my original series converges by the direct comparison test. On this problem, trying to figure out the convergence of this thing, just a quick look at this. I mean, it goes to 0 if you take the limit as n approaches infinity, so we don't get out of it that easily. But we're pretty sure this thing is going to diverge because the harmonic series, which is just 1 over n, diverges, and this thing is even bigger than the harmonic series all around. So because of that, I'm actually going to try a comparison with the harmonic series on this one. So I'll compare this to 1 over n, and I'll use the same lower limit of summation, whatever. But we know this is the harmonic, which diverges. So which comparison test should I use? Well, if I have a diverging series and I want to prove that the original diverges, the original needs to be bigger than this series I just showed diverges. Is this bigger up here? 1 versus ln of n, 2 ln of n is definitely bigger than 1 in the numerator, so that's good. And if we're subtracting in the denominator, smaller denominator means bigger overall fraction. So this series is actually bigger for n values, we'll say 8 or greater, than the harmonic series. So the way I'm going to write all this out, I'm going to say 0 less than or equal to harmonic series here, 1 over n, which is less than or equal to the original series. And again, this is true for n values greater than or equal to 8. I have to spell this out because it's not true for all n values. But now that I've shown my original series is bigger than a known diverging series, I've shown the original also diverges using the direct comparison test. For this problem, it looks like I've got a series I'm trying to figure out the convergence of, and we've got kind of a 1 over square root of n situation. This is going to behave similarly to 1 over the square root of n. So I'm going to compare it to that series. There's really no other easy, quick way to do this problem. Now this series right here is a p-series with a p-value of 1/2. Since that's less than or equal to 1, our comparison series diverges, it turns out, by the p-series test. So now I have to figure out if I'm doing direct comparison or limit comparison. Well, for direct comparison, if my comparison is diverging, that means I would want my original to be bigger than the comparison series. The numerator is definitely bigger. 4 is bigger than 1. But in the denominator, you've actually got a larger denominator than the comparison. Bigger denominator means smaller overall fraction. So we're getting mixed signals here from the original series, which means to be on the safe side, I'm going to need to use limit comparison on this. So for that, I'm going to need to verify that my original and my comparison are both greater than 0, and they are. If n is greater than or equal to 1, there's nothing negative over here or here. So I can say these are both greater than 0 for n greater than or equal to 1. And now that I've verified that, I'm going to go ahead and take the limit as n approaches infinity of the ratio of these two series. So this stuff will be in my numerator, and I'll have the comparison series 1 over root n in the denominator. All right, let's multiply by the reciprocal, same change flip. In my numerator, I've got 4 radical n, and in the denominator, I have the radical 6n plus 10. Now, as n approaches infinity, I can forget about this plus 10 inside here. I still have the square root of 6n, though, which I'm just going to take a moment to split up into radical 6 times radical n. Now that I've done this, I can clearly see that these radical n's are canceling, so I just end up with a limit of 4 over radical 6, which I'm not going to bother simplifying. The important piece here is that this is a positive finite number. It's a number, it's an L value. I labeled this as all L. This is an L value between 0 and infinity. Therefore, since my comparison series diverged, I'm going to write that my original converges, or diverges rather, by the limit comparison test. On this problem, I'm trying to figure out if this series converges absolutely, conditionally, or not at all. So I will first consider the non-alternating version of this, the absolute value of this series, just n to the 5th times 1/2 to the n. And for this one, if you try the nth term test, I mean, you've got, basically, this is n to the 5th over 2 to the n. It's bottom heavy, so it goes to 0, so that's not helpful. But since I have exponentials and it's not quite geometric, I'm going to try the ratio test on this. That might help me. So let me take the limit as n approaches infinity of absolute value of n plus 1th version of this. So we'll do n plus 1 to the 5th, and we'll also multiply that by 1/2 to the n plus 1. And in the denominator now, I just got the nth term of this, so n to the 5th, 1/2 to the n. I don't have to do any same change flipping here. It's already just a single fraction. I can reduce these 1/2 powers, though. Subtracting my exponents, I end up with just a 1/2 in the numerator. So I can actually rewrite this whole thing then as n plus 1 to the 5th in the numerator. And if I have 1/2 in the numerator, well, that's really the same as having 2 in the denominator to go with that n to the 5th that's still down there. And now I see as n approaches infinity, this plus 1 goes away. So we just have n to the 5th over 2n to the 5th, which is just 1/2. Since that's less than 1, That means this is going to converge by the ratio test, and since the absolute value version of this thing converged, we will say this series converges absolutely by the ratio test. On this problem, I want the interval of convergence for this series. All right, so since this is not a geometric series, at least not quite, we're going to have to go ahead and use the ratio test for this. So let me set up the limit as n approaches infinity of the absolute value of, and now we have a huge fraction. In the top we have the n plus 1th version of this. So x to the n plus 1, square root of n plus 1, 3 to the n plus 1. Although these n's I could merge together, this is really n to the 3 halves. So I can say n plus 1 to the 3 halves then, instead of writing more n's than I need here. Now in the denominator, I'm going to end up with just the nth version of this. So x to the n to the 3 halves, 3 to the n. And now let me flip this thing to start simplifying it. In the numerator, I have x to the n plus 1, n to the 3 halves, and 3 to the n. Denominator, I've got n plus 1 to the 3 halves, 3 to the n plus 1, and x to the n. Let's simplify this a little bit. So these 3's can cancel out, leaving me with just a 3 in the denominator. X's can also cancel somewhat, leaving me with just x to the first power in the numerator. So upstairs I have an x and an n to the 3 halves. Downstairs I still have an n plus 1 to the 3 halves and a 3. As n approaches infinity, I can forget about this little plus 1 in here. So n to the 3 halves cancels the other n to the 3 halves, and I'm just left with absolute value of x over 3. So let's set that less than 1 now that my limit's gone here. Multiply both sides by 3, so I have absolute value of x is less than 3. And to get my rough draft of my interval of convergence, I'll just rewrite this without absolute value. So negative 3 less than x less than 3. But I have a question mark here because I also need to test convergence at the endpoints. With ratio test, you never know if those endpoints converge or not without directly testing them. So let's say that x is negative 3. What's that do to this series up here? Well, I have a negative 3 to the n over a 3 to the n. That leaves me with a negative 1 to the n over all this stuff, which I'll continue to write as n to the 3 halves. So this is a series that is alternating, and since my limit as n approaches infinity is 0, it's also decreasing in absolute value to 0. That being the case, I know that this converges by the alternating series test. All right, on to the next now. X equals 3. If x equals 3, we've got 3 to the n over 3 to the n, which just cancels. So that just ends up being the series 1 over n to the 3 halves. Now this series is a p-series with a p-value of 3 halves, which is kind of nice. That's greater than 1, which means that this is going to converge by the p-series test. So both endpoints ended up converging. Either one of them could have diverged, though, so you never know. But since they did both converge, I can rewrite my interval of convergence as negative 3 less than or equal to x, because we converge at negative 3, and less than or equal to 3.